Welcome to our ORS presentation. Our ORS team is high-resolution imaging and object detection for NASA's JunoCam. Our PhD mentor is Amoree Hodges, and our faculty advisor is Dr. Paul Steffes.
I'm Alison Kennedy.
I'm Caleb Page.
I'm Gracen Wallace.
And I'm Cory Wang.
Now for some background for our project. So in 2016, NASA's Jupiter satellite Juno had arrived in orbit around Jupiter after a 5-year journey. On board the Centaur spacecraft is a multitude of scientific instruments, including the JunoCam, which is a public outreach camera put on the satellite. Our team is focusing on this instrument, and we are focusing on enhancing and documenting a lot of the current image processing techniques that are in our world right now to help interpret the scientific data found within the specific images that the JunoCam is taking. And so the techniques that we're focusing on is deconvolution, algorithms, super resolution, and object detection. So before I can talk about any of those things, all of those processes involve a data set, whether it be for training or just the source of the images themselves. For most of the year, we use images taken from the JunoCam website because it's public, and that's what these images were originally for. And so all these images that were used and manipulated for the image processing community was uploaded, and we used them for our different convolution algorithms and such. As we got in later in this year, this semester, we decided to make our own data set. That way we have more control over the images and the different qualities that they have. And so to do that, we have to get the raw data from a image processing software called ISIS-3. From there, we were able to get different framelets of the images and composite them together in Photoshop, and then color correct them, as you can see in the 2 images in the bottom right of the screen.
So after obtaining these images, the next step is to improve the quality of them by further processing and scientific investigation. So because of the way cameras blur images, each image can be mathematically modeled as an ideal image convolved with the point spread function, or PSF, which is generally unknown. Deconvolution algorithms attempt to reverse this process, and the 2 we investigated were the Weiner filter and Richardson-Lucy algorithm. The Weiner filter is essentially an optimization process. It is an attempt to find the PSF through minimizing the mean squared error between the input, which is a noisy image, and an estimate of a known image. The Richardson-Lucy algorithm, on the other hand, focuses on the PSF and is essentially an iterative procedure to generate the correct PSF recursively with inputs as the blurred image and the initial guess of the PSF. So the next slide will show sample results of our MATLAB implementation of the 2 deconvolution algorithms. So as you can hopefully see, the Weiner filter generates an output that is considerably less blurred than the Richardson-Lucy result. The mean squared errors show these as well, where the Weiner result is basically an order of magnitude lower than the Richardson-Lucy result. This may be because the Richardson-Lucy algorithm does not necessarily converge, so we have future plans to improve this process through a Monte Carlo simulation to generate an initial PSF that has a guaranteed convergence.
So similar to deconvolution, super resolution is a method for restoring images and improving image quality. Super resolution is a fairly new subset of neural networks being used to improve images. And the way this works is the neural network reconstructs an image and estimates the data between points in an image to increase the resolution by adding more detail. Currently, the most common method for training these networks is using image scaling to create a lower resolution image from an original image. This creates an ideal outcome for the neural network by using the lower resolution image as the training set start, and then the original image as the high resolution outcome. This isn't necessarily ideal though, just because this is estimating error based on known changes in images, whereas in a real world situation, you would be estimating an error on an image but not knowing the outcome you want. When it comes to Juno, super resolution will be particularly useful because right now, the image editing process to improve quality is manual, which takes a lot of different time, as well as improving image quality will be especially useful for analysis and object detection. So for the implementation being used this semester, first I'll start with a data set. So the data set being used is the div2k data set, which consists of high quality images that are downsampled to make a low resolution pair, similar to that method I mentioned on the last slide. For development, we've been using the MATLAB Deep Learning Toolbox just because it provides layer functionality as well as the ability to create custom image training systems. When it comes to the data in our neural network, luminance has been the main focus because when it comes to human vision, it's more sensitive to changes in brightness than in color. So the focus on luminance means that the change in outcome of the output image will be more noticeable. And then to briefly go into the different layers, we have an input layer that takes in that original image, a 2D convolutional layer that moves element-wise through the matrix, changing it, the rectified linear unit layer used as an activation function, and then the regression layer as an output layer. So here are the preliminary results of the neural network. There aren't very many stark differences right now just because of the infancy of this method. However, I hope that you can see the difference between the two, where there are more distinct edges to objects and less blurring. So with that, I'll pass it off to Gracen to discuss object detection.
So our final topic is object detection. And originally I began with template matching, which is just a really basic form of object detection using convolution and correlation. So as you can see, the equation kind of illustrates the mathematical idea behind it, but the process itself involves converting two inputs, an original image and then a template image, which is just a cropped image of an object from the original image that we want to identify using the algorithm. So these are converted into grayscale, and then the mean intensity of each image is calculated and subtracted out to kind of get rid of any abnormalities that would affect the outcome. Then the template is flipped and convolved with the original image to kind of emulate correlation, stemming from the proof behind template matching, which begins with the idea of mean squared error. So template matching yields a different colored version of the original image that's made up of intensity levels, where the highest level intensity in the image signifies the most likely location of the object in the template. So on the screen, you can see one of the original images that were put through the template matching program. So on the right, we have the original image as well as the template. And then on the left is the output of all the intensity levels shown on the original image. And as you can see, the purple dot where the highest intensity is present is the location of the template that we're looking for. You can also notice that there are some purple spots on the side that were kind of noise that a lot of the images had that were difficult to deal with, but when looking at the actual intensity values and the numbers themselves, the dot actually did have the highest intensity value in the image, regardless of the noise located on the edges of the planet. So object detection, now we've moved on to a convolutional neural network. So that would be using different layers, including convolution with a ReLU activation layer, max pooling, flattening, and dense layers to identify different distinctive objects on the surface of Jupiter, notably the string of pearls and the red spot. So this was implemented using TensorFlow 2.0 and a prepackaged Keras library to develop the initial network, which was then tested using the CIFAR10 dataset and tweaked to make sure that the validation levels and the test accuracy levels were as high as possible. The eventual goal is to train on a large set of Juno images and then be able to use binary image detection, basically to identify whether or not a pearl from the string is present in a given image.
So here are our main results for our work this semester. And as I mentioned earlier, the mean squared error from our Wiener deconvolution filter is 0.0037, compared with the mean squared error of the Richardson-Lucy algorithm, which is 0.0197, which is about an order of magnitude higher. So at this moment in time, our implementation of the Wiener filter is a better algorithm for deconvolution.
Next, we have the results from the CIFAR10 dataset on the convolutional neural network. So as of right now, the training accuracy is really high at 96%, and the validation accuracy is steadily climbing, but currently at 70%.
Looking forward to the progress our team hopes to make. That'll first be with creating our own data set. We want to create a full planetary data set for training the neural networks, just so we can improve that accuracy and precision when it comes to training. Next, we hope to have a full sub-team dedicated to improving the dataset images. Currently, this is being done manually, but we'll provide a data set that isn't reducing the quality of the original satellite images. And finally, we hope to test the object detection neural network on NASA's planetary data system so that the known features of other systems can be used to evaluate accuracy. And with that, this is what our team has gotten to work on in the past year. We look forward to continuing in the future, and please feel free to reach out with any questions over email.